Okay, so I've done this presentation 1 month ago, and I ran badly out of time, so I've got a lot of stuff to say, and I know that some will not fit. That's not a problem, so I've moved things around so that I will say today things that I did not say last month. And I will talk about BearSSL, which is an SSL library. So the outline answers the first question of why another, and then I talk about constant time implementation and all the challenges about implementing SSL in constrained RAM, because that's the focus of that implementation, and a few considerations of XSNF certificates, which are pretty horrible. And then, if time allows, I'll try to describe a lot of existing SSL attacks and how an implementation can strive to avoid them. And finally, why SSL is that kind of protocol which is in need of replacement by something saner. But that's maybe for another day. So, about 2 years ago, I woke up one morning and I told myself, today I will write another SSL library. And it took me a little more than a day, but now it's done. So in order to understand why, first a couple of slides to explain just a refresher of what is SSL. SSL is now known as TLS. I'm using the term SSL to designate the whole family. So the change from SSL to TLS is a change of ownership. The SSL versions were owned by Netscape, and the TLS are designed by the IETF. So it's more a question of marketing than technology. That's why I use SSL for all versions. But in practice, SSL 1 and 2 and even SSL 3 won't be implemented. So whenever I say SSL, you can feel free to understand it as TLS. So SSL is basically plumbing. Whenever two machines must talk together over potentially hostile networks, they need some sort of protection against passive, eavesdropping, and active attacks. And SSL is the most well-known protocol to do exactly that. That is, it takes as input some reliable transport for bytes, bidirectional streams. And by reliable, I mean that if there's no attack, ultimately all bytes will go to the right destination with no duplicates and in the right order. So you can imagine a TCP connection, which that's exactly what it does. So when there's in a non-hostile context, you get your bytes from one client to server and back. And then SSL provides security above that. That is, it takes that reliable transport and provides a reliable transport which will reliably detect alterations and which will provide confidentiality. So in HTTPS, the S does not stand for SSL. It stands for secure. But the first S of SSL is secure. So it really is HTTP in SSL. In other protocol, SSL must be invoked explicitly. For instance, in SMTP, you've got the start TLS command and so on. So it's an important element for transport security. It does not do everything in security. If your server has SQL injection vulnerabilities and it's powered by SSL, then you'll get SSL-powered injection vulnerabilities. That won't solve it. But at least if you do not have such a reliable, secure transport protocol, a lot of things that you would like to do are doomed from start. So it's important to have it. That schematic is the core of SSL. It means that whenever you want a client and a server want to talk, there is this handshake, which is a protocol with messages exchanged in both directions, that ultimately agree upon cryptographic algorithms and keys to use to do encryption in the application data. So what you must understand from that point is that the client is the one that talks first and sends the client hello, which basically says what the client can do, and then the server will answer with the server hello, which answers what the client and server will do. That is, the client will offer a number of cryptographic algorithms, and the server will choose, and so on. The messages with a star are optional, so it depends. The server may ask, for instance, for a client certificate, but it may also not ask for one. So the implementation must be able to react to the flow of messages which are exchanged. So it's a relatively complex protocol, and to get it right, you have a number of options to take care of. So these things are technically known as things. These are a rising category of objects which are internet protected. So on the upper left, you've got something which is called a Kevo lock. It's basically a door lock that you can open with your phone. So you understand that there's some security issues so that only your phone may open the door to your home. On the upper right, there is a security camera, which you put again in your home and which will propagate pictures from the inside of your home to the world in general. So you generally want it to be restricted in some way. Other things are the light bulbs on the lower left, which can be controlled from from your phone or even from a very remote place, so that, for instance, I'm in Montreal. If I had those light bulbs, I could light up my house from here. And my house is in Quebec. It's 250 kilometers away. And people do that. Don't really know why, but they do that. And on the lower right is yet another connecting things. It's called the moo call. It's the green part. In fact, that device is meant to warn the farmer that a new call is about to happen. That is, that call will soon spawn a new veal, and when the interesting things happen, the farmer must find the cow back and get the veterinary and some help so that it goes smoothly. So basically, that cow is internet connected and will talk to the outside, also reveal its location. So it's really an internet, it's a server, it's on the internet. So all those things are in need to do some secure communications, so you would like to run some SSL on that. Unfortunately, there was no SSL library which could do all the stuff listed here. That is, a library which is really correct and secure, which works on systems which have very little RAM, so I'm not talking megabytes here, but rather 25, 30 kilobytes. It should be small also in terms of size of code. It should be able to run on systems which do not have an actual operating system. That is, just like your NorthSec badges, that kind of systems is bare hardware, and you don't have an operating system, you just, the code must issue command to the hardware directly. So a library that runs on that kind of hardware should be able to run without the luxury of having threads or system calls to open files or so on. And since it should run on embedded system, it should run with the tools which are used on embedded systems. This is basically a C world. So we're not talking about Java or Rust or anything which is more meant for bigger computers and not yet ported to small systems. There are a lot of existing SSL libraries, OpenSSL, of course, and its derivative like LibreSSL, BoringSSL, but also smaller one, including EmbedTLS, which was called Polar SSL, and it's meant for embedded systems, but it's not as small as we would like. It requires about 50 kilobytes of RAM, and it needs some OS support, and so it's not as small as I would like. So I decided to write a new one, just basically to show to the world how such things should be done. There's a lot of hubris in that. I'm totally aware of it. So I wrote it from scratch. I wrote it in C, mostly. There's a twist we'll see later on. And I wanted to fit in 25 kilobytes of RAM, about 20 kilobytes of code. That one is not a success. I am at 21 kilobytes of code, but I'm working on it. And I wanted it to use no dynamic memory allocation whatsoever. So there's not a single malloc call in everything. It uses static size buffers provided by the caller, and it tries to do anything in that. And this means that I can claim with full certainty that this library is one of the rare libraries that have correct memory management. I mean, since I don't allocate anything, it's obvious that I did not forget to free anything. There's no memory leak. And it looks like a gimmick, but it's important. When you have your system which is attached to the core and just working through the fields, you don't want it to crash needing a reboot because it has run out of RAM. So having correct memory management is an important feature. And it's a bit extreme to completely ban dynamic memory allocation, but it works. And I also wanted it to have a state machine API. A state machine API means that you're not using the library with a simple read call, telling to the library, connect, do your stuff, and then give me the bytes, because that would be blocking. Instead, it's a state engine in which you push data that you would like to send, or bytes that you received from the network, and then it provides bytes to send to the network, or application data which has been received and decrypted. So we'll see later on how it looks like, but it's meant for better integration in a system which does not have an operating system, does not have threads, and still must do several things more or less simultaneously. So I wanted some extra goals, because why not? So I wanted all the cryptography to be pluggable so that new implementation could be substituted for specific platforms. I wanted all the code to be clear, documented, and possibly to serve as an educational tool so that the source code could be shown to potential students and we could tell them, read that, you will learn. And of course, I wanted it to be open source and reusable. It's an important characteristic in that there are some small SSL libraries which have difficult licenses. By difficult, okay, it's a bit inflammatory, but I mean they are usually either GPL or proprietary or both. So if you want to reuse it in your system, you must either pay or show your own code. And in practice, a number of vendors of embedded hardware don't want to buy things because they like to keep their money, of course, but they don't want to show their code either. So there was somehow a need for a library which would be MIT licensed so that anybody could reuse it without thinking about these problems. Okay, and of course, I needed to support many algorithms because the point of using SSL is to be able to interoperate with existing implementations. So it should be able to connect to existing servers, which have various configurations. And finally, the library should work on small systems, but also on big systems, and it should work reasonably well. So there's a lot of cryptographic algorithm that I have implemented. So it supports RSA up to 4096 bits. See the hard limit because it's the size of an internal buffer. But arguably, anything beyond 2000 bits or so is useless unless you want to impress an auditor. But it won't bring more practical security because RSA with 2000 bits is already far beyond that which can be broken with existing algorithm and technology. So I also support elliptic curves, the nice curves and the new fancy curve, curve 25519. With the X, it means that it's Diffie-Hellman over that curve. Also AES and Cha-Cha-20 and Cuption and so on. And I included some support for triple-des and SHA-1, just in the interest of interoperability, but I keep it at the bottom of the list. Every time a client and a server supports several cipher suits, there's a preference order, so I put triple-des at the very bottom of the preference order, so that it gets used only when that's triple-des or nothing. And arguably, triple-des is better encryption than no encryption at all. So, constant time cryptography, it's a relatively new thing. It appeared around 2005, really in earnest. The first attacks which were related to side channel leakage for timing were published in 1996, I think. And then it developed, and it has become now a rather constant theme, in that having good algorithm is a nice thing, but when you implement them, there is a possibility that some secret data, especially the secret key, might leak through how fast the speed of execution of the algorithm, or how it impacts the speed of execution of other operations on the same systems. So a lot of interesting demonstrations have been done in the lab, and there has never been, as for now, an actual use of timing-related leak to crack a system observed in the wild. It is with code, we have code which works, some demonstration. It seems important, but right now, real attackers who do that for profit don't do that. They will one time, but they still have easier paths in practice. But when the last SQL injection has been finally killed, then attackers will try to break cryptography, and they will try these timing attacks. So, timing attacks are a subclass of all side channel attacks. Side channel attacks are about leak of information from outside of the abstract model of the execution of the algorithm. The algorithm has a mathematical description, and it says you get this on input, you will get that on output. And every piece of information which flows to the physical world outside of that abstract model is a side channel. So there are many possible side channels, such as, in particular, energy consumption. It's called power analysis, and it's a very efficient tool to try to break the cryptography in smart cards. But one of these channels, which is the exact timing of operations, has the unique property of being observable from remotely. That is, if you are trying to do power analysis on a smart card, you have to be physically in the same room of the smart card. You must interact with it. But a timing attack could be done from another country. So for anything which is connected to the internet, and anything which does SSL must be using some network of some sort, because otherwise SSL does not make sense at all. So anything which does SSL is a potential target for timing attacks. So execution time can vary on there are several classes, in fact, of leaks related to timing. The algorithmic timing attacks are basically every time you get an if in your code. If you execute some part or not, depending on secret data, then the execution time will vary depending on the condition for that if. Then the second class is called the cache-based attacks. This is whenever your CPU is doing memory accesses, for instance, lookup in tables or in code paths, That access may take some varying amount of time depending on whether the data was in cache or not. But also, even if you can assume that the data was not in the cache at that point, so it will be a cache miss, then it may move away from the cache some other data. So it may imply a timing leak for some other operation, non-cryptographic operation, which will be done later on the same hardware. So you can have some indirect leaks. And finally, you have some specific operation, in particular integer divisions, or in some case multiplications, which are not constant time, and whose execution time will depend on the data which is processed. So these three classes of potential timing leaks must be avoided when you are trying to implement a cryptographic algorithm and you want a constant time implementation. So let's see the case of RSA. RSA, a classic implementation is a modular exponentiation. So you are using a square and multiply exponentiation in which you are doing a lot of modular squarings and some extra multiplications which correspond to the bits equal to 1 in the secret key. So this is a conditional path. That is, if the secret qubit is 1, you are doing an operation that you are not doing if it's at 0. So the overall execution time will leak some information on that secret data. So it's a posterior case of a timing attack, and that's what was published about 20 years ago. So one solution which have been employed by many libraries is to do some random masking according to these equations that you can read if you like mathematics. And if you don't like mathematics, I won't explain it to you because you would be bored. So, and the problem with that masking is that it requires a source of randomness, and randomness is a hard requirement, especially in embedded systems. So another solution is whenever there is a conditional operation to perform, is to always perform it. And then doing a constant time choice between the unmodified data and the modified by the operation, and to choose one, but always reading both. So in terms of code, it will look like that. So this is a constant time lookup in a table. Yeah, I've got that. Here, I've got, in that T2 variable, I've got a lot of pre-computed values, and I'm selecting one of them based on a special secret value, which is bits, which is exactly what it's named. It's a sequence of bits in the key. And I'm reading the complete table, but I'm using a special masking value so that I'm doing a bitwise AND with everything I read, bitwise AND with a mask which will be 0 almost all of the time, except for the one value which I need. So from the memory access pattern is always the same. I'm always reading the whole table, but in fine, the value I get is just one of them. But from the point of view of the cache, all the memory accesses have been performed, and nothing depends on the secret bits, so nothing has leaked. And then I'm using the value which I recovered in here. Here, these are the squarings. I'm multiplying value x by itself. It's modular, so there's a lot of mathematical stuff behind, but it's a squaring. And here I multiply the results of all these squarings with the value I've looked up from the table. And so this is completely constant time. And so I have an RSA which does not leak information, so timing, and which does not require a source of randomness. So RSA was relatively simple in that sense. So now we're talking about other cache-based attacks, and especially in AES. AES is an encryption system which is well designed. Mathematically, it's elegant, but a normal implementation will use lookup tables, and the slots which will be read will depend on secret data at each point. So some lab demonstrations have shown that it was possible if you have two processes running on the same system, or even on the same hardware, so they could be from different virtual machines on the same hardware. One of them is doing some encryption, and the other process does not know what is being encrypted, neither the plaintext nor the ciphertext, but it can still work out the secret key which is used. So the key is leaking even across virtual machines. So, of course, on small embedded systems, I won't have several virtual machines, but you can get the same kind of problem if once the encryption has taken place, and the hardware may respond to a network query, and which will exercise the same memory, the same cache. So one possible difference for these cache-based attacks is something which is called microarchitecture defense. It's basically making extra accesses so that all cache lines are populated. So it's some trickery that depends on your precise knowledge of how the cache works on the hardware you are using. It's hard to do because you usually do not have an exact description of how your hardware works, because the hardware vendor won't tell. I mean, the best you can have is the hardware, what's the name? The manuals. The hardware manuals from Intel or AMD, which give you a lot of information, some of which is wrong. Sorry. And of course, whenever you've written your code, even if it's nice and it hits all the cache line and does not leak on the specific hardware you have developed, then a new version, a new subversion of the hardware is produced, and you move your code to that new version, and it does not work anymore. So that, more than that, functionally it will keep on working, but it will leak information. So you won't know it. So that's why I say that it's a fragile way of doing things. So the true constant time is to perform no secret dependent memory access. That is, the address of the memory access won't depend on anything secret. And also no secret dependent conditional jump and so on. So one tool for that is called bit slicing, which was discovered by BIAM about 20 years ago now. And it's a sort of new way of implementing algorithm by thinking about that as if there were some hardware circuit. So for instance, if you've got a 20-bit value, instead of putting it in one variable, you are spreading it over 20 variables. It will take 1 bit in each variable, and then everything you implement will be bitwise operations like XOR and AND, as if you were taking a whole circuit and translating all independent transistors into C operations. So for instance, this is just an illustration. Suppose that in some algorithm, you've got two 6-bit values, you must XOR them together, and then rotate left the result by 1 bit. So on the left, that's the classical implementation. You do a XOR, then this is a rotate, some shifting and masking and OR to do that. So the bit-slice version, we look on the right. On the right, you see that you have now 6 bitwise XOR because you've spread all 6 bits into independent variables. So you have to do the 6 XORs. On the other hand, the rotate has disappeared because it's merely a problem of routing data, that is, of taking the right variable. So you see that the results are numbered. Okay, move on. Sorry. So the results are variable z from 0 to 5, but it's actually 1 to 5, then 0, because it incarnates the rotate. From the face of it, we just replace 5 operations on the left with 6 operations on the right, so it does not look like a big gain, but There is an important speed bump in the bit-slice operation, which is that it's parallel. That is, my variables here are not single bits. There are words with 32 or 64 bits. So whenever I do the XOR between X0 and Y0, I'm actually doing 32 or 64 exclusive ORs. So what I'm doing in the bit slice operation is that I'm doing 32 or 64 parallel operations. That is what I do on the right with 5 opcodes. I'm doing 32 or 64 times that operation with 6 opcodes. So it's, in fact, extraordinarily faster if the operation I have to perform can be made in parallel. That is, if I have many identical operations to perform simultaneously, with the bit-slice representation, I can do that efficiently, and moreover, it's necessarily constant time. Because since they are done in parallel, there's no way that the opcode I'm submitting to the CPU will depend on the data, since it should work for all of them. So it has been called orthogonalization of data, because if you want to represent it in matrix notation, it's a transposition. You have to move data in such a way that what you thought as several variables become several bits in a variable, and vice versa. So it looks good, but it has also some problems. That is, it will use more RAM, more code, it can make really big code, and some operations such as lookup tables, which will be used in the ES, become very complicated circuits. So it's not a matter of 5 or 6 XOR, but rather a few hundreds of them. And finally, there are some contexts where you do not have several operations to perform in parallel. CBC encryption, not decryption, but encryption, is typical in that when you are doing CBC encryption, you process data block by block, and the output of the encryption of one block is used as input for the next block. So you can't do them simultaneously, since each one depends on the result of the previous. However, it's possible to do some mixed strategies in which you are trying to exercise internal parallelism, and you have that in AES. AES is layered as a number of wounds, and each wound contains a number of operations, and one of them is applying the S-box. S-box is a 8-bit to 8-bit lookup table, and you've got 16 identical S-box that work on 16 bytes, and it does that in parallel. So that's a good opportunity to try some bit slice which will compute these 8 S-boxes in parallel. And that's exactly what I'm doing, and I'm not showing the code for the reason that it's very long. That is, it won't fit on the screen. But in fine, I got some ES which is constant time, slower than a table-based AES, but not terribly slower. I mean, we're talking on a 64-bit machine, we're talking that it's about 55% of the speed of a normal AES. So we are down to about 80 megabytes per second on a big PC, which is really sufficient for many uses. And this specific AES implementation has been included about 2 weeks ago in the OpenBSD system. So it's now the default AES encryption in the OpenBSD. So for constant time cryptography, there are still some tricky opcodes that must be avoided. So we talked about memory accesses and conditional jumps. Integer division is a big no-no because it's never constant time. On some architectures such as ARM, there's no integer division at all. That is, it's a function. So if you want to know if it's constant time, you have to look at what the C compiler is producing for a division, and it's not constant time. And you must make some care about shifts and rotation. That is, when you are shifting or rotating some data, the execution time may depend on the shift amount, not on the data which is shifted or rotated, but on how much you are shifting it. Famously, the Pentium 4, which is already 15 years old, but that was a processor which did not have that hardware piece called a barrel shifter. And if you are doing a rotation by some amount of bits, it could take longer for higher amount of bits. And this impacts some cryptographic algorithms where there are rotations with non-fixed amounts, especially RC5, if you remember that. And finally, there are integer multiplications. And on some processors, most PC, it's constant time. On some others, it is not. And on some embedded systems, especially the ARM Cortex M3, it's supposedly constant time, but it's not. That is, it's one case where the hardware, the manual from the hardware vendor is false. It states things which do not map to reality. So I'm trying to keep track of which architectures have constant time multiplication. So you are invited to read that page and to contribute if you have some extra information on the subject. So another point which I would like to talk about is streaming and buffering. A whole lot of writing an SSL library is to be able to process data and to handle it as it comes in streaming. So for instance, consider the first message which comes from the client sent to the server. It's a client hello. What you should like in this description, what you should see, is that it's a nested structure, so it contains some substructures, including one which is called extensions, which is a list with a number of substructures, and it's all nested. And similarly, the client will need to validate the certificate from the server, and here is a description of the format of a certificate. So it's a very small part of the description, but there again, you've got sequence, which is called it's a structure, which contains other structures, which themselves contain other structure, and in the encoding, each substructure will have its own length and contents and sub-elements. So what's to be understood here is that if you want to analyze such a structure, it's much easier if you can have it all in RAM in one piece, because then you can just walk through it with a function and sub-function that pass the various pieces. That's the solution which is called buffering. So basically you allocate some RAM to get a complete message or a complete certificate in one go. So that's exactly what OpenSSL does, but the maximum message size is about 16 megabytes. That's because the length of a message in SSL is encoded over 3 bytes. So it could be up to 16 megabytes. And theoretically, you could send to a server a message header saying, okay, you'll get 16 megabytes, just allocate that. So since it has a rather high potential for denial of service, OpenSSL will enforce a smaller and thinner limit. That is, it will refuse any message which would require more than 64 kilobytes. Now remember, I wanted no malloc and to fit in 25. So buffering is a bit out of the question for BearSSL. So another way to process that data is exactly what you would do in modern languages such as, I mean, not so modern like Java or C# or more modern, in which you have basically stream abstraction. So you can write code which will read bytes, and whenever it reads, it needs some extra bytes to parse a structure, it just calls a read method to get the next byte. And of course, if the next byte has not been made available from network, this is a blocking call. So the thread which is waiting for the next byte will wait, other threads will run until everything has happened. Now this needs blocking operation and threads, so basically an operating systems, and each thread will have its own stack, so you have a big computer with RAM and an operating system, so it's not a solution which is applicable to my context. What I would really want is something which is known as coroutines. A coroutine, you can imagine that as being another thread, but which does not run concurrently with your own code. That is, you have several coroutines, and at any time, only one of them is progressing, and when it needs to call another, the CPU jumps to the other one and won't come back until that other one has decided. So if you have coroutines, you can make a state machine API in which the decoding engine will be invoked by pushing some bytes as received, and then it will come back, but still be alive as a coroutine, and telling you, give me the next bytes when you have them. So if your library is implemented as a state machine, you can stream data, and it's the library itself is purely computational. It does not perform input-output. It reacts to data you push, and it produces some other. So you can then, even if you do not have an actual operating system, you can handle several stuff at the same time, because none of them will be blocking. Now, the main problem is that in C, you do not have coroutines. It's possible to do some dirty hacks to make sort of coroutines with set jump and long jump, and it's at truth, and it needs bigger stack, and it won't work on small systems because it requires a little bit of extra support from the system. So this is how BearSSL API looks like. So there are 4 pairs of functions, and each pair will give you the address of a buffer. This one, send app buffer, means the buffer where you can write application data that should be encrypted into the SSL tunnel and sent to the peer. So BearSSL engine send app buffer will return you the buffer where you can write such data, and will write in line how many bytes can be accepted at that time. And when you have written some bytes in that buffer, you call the other one to tell him, okay, I've written len bytes, do your stuff. So there are 4 pairs. The first 2 as for plaintext, the application data, and the other 2 are on the other side of the engine, that is, the bytes that must go on the network. So from the caller, none of this call is ever blocking, and it's the job of the caller to talk to the Wi-Fi, Bluetooth, serial line, or whatever mechanism you use to move bytes around. Okay, I do not have coroutines because that's C, so the solution was obviously to invent a new programming language, because why not at that point? And okay, it's not pure madness, because it was basically a derivative from a very old language known as Force, which was invented in the 70s to drive automatic telescopes. An astronomer called Charles Moore invented that. So my language, which I call T0, which has absolutely no meaning whatsoever, is basically a Force dialect, which are then mixed with some things which are absolutely non-Force, which is that, for instance, it has a separate compilation. In true Force, it's interpreted and everything runs on the same hardware, which is both the development system and the production systems at the same time. Having a separate compilation is not something which is normal in Force, but I still did it. And since I had to play with 2 languages, I wrote the compiler in a third one, which is in that case C#. And And basically, well, it looks like that. Okay, it's a bit barbaric, but it's a stack system. So each operation, each word that you see here is basically about pushing something on a data stack and calling a function. So this excerpt is about processing bytes from the peer which appear in special SSL messages which are called alert messages. So what must be understood from here is that each word is translating to a sort of opcode in an interpreting system and which fits on 1 byte. So this code will take about 40 bytes of code space. It's very compact. And it's with some experience, it actually reads like a normal programming systems. So you have to think with the stack, and it's a reverse polish notation. So for instance, that dup is duplicating the top of the stack. One is pushing another value. This operator is taking the 2 values on the top of the stack and seeing if they're different or not. If is doing a conditional jump based on the result, which stop on the then. The then is after what you're doing. So one thing that we are completely losing is that in C you've got some type analysis. The compiler will remember which variables are int or pointers or so on, and if you take an integer and use it as a pointer, it will emit a diagnostic, that is a warning or an error. When you're doing force, everything is a 32-bit word, so you don't have that. But still, I've implemented some sort of type analysis. Rather, it's a stack depth analysis. That is, the compiler is able to determine the depth of each call at each point of the code, and can do that statically. So in my case, this is for the piece which is parsing X509 certificates. It's guaranteed that it won't use more than 17 slots on the data stack and 25 on the return stack, because it's a 2-stack machine. So I've got strong guarantees of memory usage, and these are actually stronger than what I can get with C. So I can claim that it's in some way a bit safer to code in that forced DLX than to do it in C. Now, safer does not mean safe. So for instance, this is an excerpt where I had an actual bug which could lead to a real buffer overflow and remote code execution and so on. And it's a bug which has been discovered amazingly by an automatic leap further, which was called leap further. And the bug was just here, that 7 was an F. What I was doing was that I was decoding a length, which is an element in the encoding of a certificate, to know how many bytes were there. And I wanted it to fit on a 32-bit variable, so I was checking for overflows. But I was checking for overflows assuming an unsigned 32-bit system. But in the rest of the code, I was using that length with a signed comparison. And since there are no differences between signed and unsigned in my small type systems, the compiler was not seeing the problem. So the fuzzer produced a length which decoded to about 3.5 gigabytes, which is huge, and there were not that many bytes afterwards, but when interpreting in a signed way, it was a negative value. So now the rest of my code was perfectly okay for reading up to hundreds or even kilobytes of code in a buffer, which was much smaller because the comparison was using the size, it was considering that the size was negative. So this brings us to this atrocity, which is called X509 certificates. So for the best or the worst, and mostly the worst, SSL is married with X509 certificates. And in the new TLS version, they're trying to change that somehow. Basically, it's a key distribution system in which clients know the public keys of some root authorities in some way, and can use that to validate certificates which are signed entities that provide knowledge about the public key of a specific system. So BearSSL has a pluggable support for extension X509 certificate validation, and I've made 2 implementations. And one of them might be a better idea for an embedded system, which is the known key. In known key, that's a very simple implementation which simply completely discards the incoming certificate and uses an hard-coded public key. All the certificates are meant for the server to explain to the client, to publish the server's public key to the client in a way such that the client may make sure that the public key is the right one without any prior knowledge. Now, in closed systems, and many embedded systems are closed in some way in that they already know which server they are going to talk to, prior knowledge is easy. That is, it is possible that the system has some prior knowledge of the server public key, in which case decoding the incoming certificate is completely useless. So the non-key implementation does just that, and it's therefore efficient. Now I've done another one, which I call minimal, which does the actual certificate validation with all the signatures and name mapping and decoding extension and so on. So non-key, I described it, and minimal, it has some restriction because it's small. I'm reasonably proud to tell that I could implement that specific validation in less than 7 kilobytes of code. So it's rather compact, but it can't do everything that could be expected, in particular because it does not allocate extra RAM, so it cannot even remember a single certificate at a time. It must process the certificate bytes as they come and can never have the full one. So it cannot also reorder certificates. So it must validate the certificate chain as it is sent by the server. It can support a set of transform cores, that is the caller, the application which uses the library will configure it with what certificate authority is using. And then it will check the following things, which are that all along the chain, the subject and issuer ID and match, that the expiration dates are correct with regard to the current date, with a small difficulty here, because knowing the current date means that you have a clock. Not every embedded system has a clock. So the API is that the application can push the current time on which to do the validation if it's available. But if it's not available, you have no choice that to accept any certificate as if it was not expired. Basic constraints is about distinguishing between certificate authority and non-certificate authority, and key usage is a restriction extension to explain that a given public key in a certificate may be used only for signatures or only for encryption. I also extract names from the common name and from the subject type name, because the client SSL in a web context must validate that the server certificate is not only a real certificate, but also the real certificate for the server it expects. That is a certificate which contains the expected server name as known by the client from the URL to use. So I'm extracting that information, and I'm doing all the Unicode decoding and so on, and UTF-8s and surrogate pairs, and there's a lot of complexity, and it's all done in T0. And I'm supporting the simplest case of a wildcard name when the name starts with a star.google.com. So what this does not support are these small elements, but basically revocation, all the CRL and OCSP. It won't try to download extra certificates if it will validate exactly the path received in that order and nothing else. It won't support name constraints. Up until about 2 years ago, nobody supported name constraints, but still it does not. And certificate policies, but I've yet to find a certificate authority that understood what certificate policies are about, because none of them produces anything which is compliant to the standards. And yet, it's safe because whenever there's an unsupported extension which is marked critical, the validation will stop, because that's exactly what X509 mandates. So you won't be able to make it accept a path that it should not. The problem is just in the other direction. There are paths which are valid, but use features that are not supported and will be rejected. So normally here I would talk about a number of attacks on SSL, but of course, as predicted, I don't have time, so I'll just show a summary. Here are 12 kind of attacks which have been published and described on SSL, and if you want to write an SSL library, you have to understand what all those 12 are about and what to do about it. So we talk about timing attacks. Poodle is basically means that you should not use SSL3 because there's an unfixable problem in the padding for CBDC encryption. So BearSSL does not support SSL3. It would be relatively easy to support it, but no, I won't do it. Crime is interesting in that it's a fundamental question, information theoretic fundamental point. That is, encryption is very good at hiding data contents, but not at hiding data length. And compression is a mechanism by which the length will vary depending on the data contents. So compression, which was including in SSL optionally, it necessarily leaks information on the data since it will vary the length that the encryption won't hide. So the only way out of that issue is not to support compression. So be it, no compression. DHT parameters is about usage of Diffie-Hellman, and in fact it's very hard for the client to validate whether the ephemeral Diffie-Hellman parameters from the server are correct or not. So I took the extreme case of not supporting DHT at all, but only the elliptic curve version, which are more efficient anyway, smaller and faster, and it's a way of the future. And for instance, in the Microsoft world, IIS never supported DHT suffer suit, so that's not and they survived. I mean, Microsoft still exists, so it's not a suicide not to support DHT, and so on. So I have to these slides are already up on my website, so you could see my splendid schematics. Nice drawing. So a lot of explanation of how we are doing things, and these attacks such as Beast have been published with these nice acronyms over the years. That's a current trend. 5 minutes? Okay. And for each of them, there is a countermeasure. So for instance, it is possible to implement TLS 1.0 securely, even in contents where that attack may apply. It's called the 1 and -1 split. So there is a current fashion to say that TLS 1.0 must be disabled as well, and it is expected that next year PCI DSS will enforce a ban on TLS 1.0, but it's not a bad idea to use a newer version, but it's still possible to use securely TLS 1.0. It requires some tricks, which I have implemented, and that works reasonably well. So, and last one, there are a number of cipher suits which have been defined in SSL, and especially export cipher suits, which were meant to comply with the export regulation in the United States before year 2000, and which basically were weak and purposely weak so that they could be broken. So the simple solution about weak cipher suit is don't support that. So I don't. But a number of existing libraries still support weak cipher suit, and they have been broken, and that led to to real attacks. So I've got 2 or 3 minutes to just say that SSL sucks. So it's a bad protocol. It has problems, especially records. Everything you send in SSL is a bunch of records. It's organized as record, and each record is the unit of encryption. That is, whenever encryption is applied, it's on a whole record, and an integrity check, a MAC, is applied on the whole record. So from the receiving side, you must buffer the complete record in order to verify the MAC before being able to process the data which is in it. So a client or server must have the ability to buffer at least 16 incoming bytes. So if you remember, I wanted to do everything in 25 kilobytes of RAM. So more than half is just that buffer for a single incoming record. And if you want to have a full duplex policy, that is being able to send and receive records more or less at the same time, and you must be able to do that to support HTTP, because HTTP says that you can send several requests in a row. Then you'll need 2 buffers, 16 kilobytes in each direction, so 32. So for embedded systems which are constrained in RAM, for instance, the one you have around your neck has 16 kilobytes of RAM only. This is a problem. So there is an extension which has been defined to use so that the client may ask for smaller records, but it's badly defined, so it's not very usable and even less supported. So for instance, OpenSSL does not support it because it's client-driven, so the server has no occasion to enforce a smaller. So I am working with some other people on defining a new extension which will allow smaller records, but it's not done yet, and it will be some time before it's, years before it's actually deployed anyway. So there are a lot of historical craft from older version of SSL. There are renegotiation, which is an old remnant, and of older version. And TLS 1.3 is being defined recently, but it's an emphasis on the web. So it's defined with features that requires more RAM, and it's not for embedded systems. There are the cookies and session tickets which can force the client to be able to allocate up to 64 kilobytes of RAM on demand. So, and it's really designed to be a companion to HTTP2, which is meant not for embedded system, but for web browsers. So it's expected, that's a prediction not only from me, but from other people such as Peter Gutmann, that TLS is in the process of forking. That is, the new version is for the web, and TLS 1.2 will remain basically forever for the non-web applications. So if we want to make better, you would have to start from scratch, restart from scratch for a new protocol with less options, an easier to parse encoding of messages, and normalizing on smaller buffers and so on. So I've got some idea to write a new protocol, but I know it's a terrifying amount of work, so I don't want to do that right now. And anyway, just proposing a new protocol would not be sufficient to make it accepted. The main strength of SSL is that it's already there. So people can start using my library and it will interoperate. Whereas defining new protocol, it's nice, but in 10 years from now, they still won't be used.